right, so on to the R package. So we've written this R package called TTI that lets you implement this model. And you can find it on GitHub or on Crayon. So you can do just the normal install.packages, TTI. And so the number of default compartments in our R package are kind of substantially more than what I've just shown you. We use a little bit more of a complex version of this mathematical model, although it's the exact same framework where we're multiplying our compartment vector times an infect matrix and a detect matrix. But now instead of having just 3 compartments, we actually have 9. And that's because we basically wanted to add some granularity to this to be able to sort of get a little bit more, hone in a little more on those individual probabilities. And so we split by whether the case is asymptomatic or symptomatic. And so this basically lets us incorporate a probability of transmission if we think that, for example, people who are asymptomatic are less likely to transmit. And we also include a designation for whether the contacts that are infected are community contacts or household contacts. And that's largely because we would expect that contacts that are sort of within the household might be a little bit more likely to be infected than those in the community. So the main function that I'm going to be talking about today is the get_r_effective_df function. So get r effective data frame is what this stands for. And so there are a lot of parameters that this takes because we are kind of dealing with a little bit more complicated model. So I'm going to sort of step through what these parameters are, and then I'm going to show you a really quick example of using it. So we have alpha, which is the probability of an asymptomatic infection. And so this is what's going to determine how likely it is for someone to be asymptomatic or symptomatic. And then R is going to be the overall reproductive number. So for example, in the example that I gave you before, that would have been 2.5. Kappa is going to be the relative transmissibility of an asymptomatic individual compared to a symptomatic individual. And so often we'd expect this to be less than 1 because we would think that asymptomatic individuals are probably transmitting a little bit less. Eta is the probability that a contact is going to be a household contact. And so this is basically, if we're under lockdown, then you would expect most people's contacts to probably be coming from their household. But if we're not in that situation, then maybe most of the more contacts are coming from the community. And so this is sort of going to be based on the community that's working through these different values. And then nu is going to be the relative risk of infection for a household contact compared to a community contact. And so household contacts are going to be more likely to be infected than community contacts on average, since they have kind of closer quarters. And then we have a whole bunch of time parameters. And so these dictate those, if you recall when we were doing our infect matrix, we were using this integral from -infinity to some t, or some time from symptom onset to isolation. And so we allow for these to be flexible depending on if the person is symptomatic, and also depending on whether the contact is a community contact or a household contact. So for example, the t_ds parameter is the time delay from symptom onset to isolation in detected symptomatic persons. And then t_da is going to be symptom onset to isolation in a detected asymptomatic person. And the same for all of these TQ values. These are all going to be for different quarantine individuals that are being quarantined. The time from the case's symptom onset to the quarantine of those contacts. And then we've got a set of omega parameters. And so before we just had a single omega D and then we had an omega Q. And now we've split this into an omega C and an omega H. That omega D gets split out to these two values. And so we've got the probability of being traced and quarantined given a community contact. And so basically whether or not this probability would dictate, how often are we tracing and quarantining community contacts. And omega H is going to be the probability of being traced and quarantined given that you are a household contact of a person. And then omega Q is going to be the probability of being traced and quarantined given that you are a quarantine contact of a person. And then we've got quarantine days, and so this is going to be the number of days that contacts are told to quarantine. The default is 14, but some countries right now are varying their quarantine times, and so you could potentially vary that value. And then we have row S and row A, which are the probability of detection and isolation given that you are symptomatic or asymptomatic. And so you might expect that maybe we're detecting more symptomatic cases, and so row S maybe would be a little bit higher than row A, for example. All right, and this is the end of the parameters list here. So the next is going to be an offset, which is basically the offset of infectiousness compared to symptom onset. And so how soon are you infectious prior to symptom onset? The default here is negative 2.31, just based on some studies that have shown that that seems to be approximately right. And then shape is going to be the shape of the gamma distribution that's used for the infectiousness period. The default here is 1.65. And rate is going to be the rate of the gamma distribution of the infectious period. And so those are going to, those three pieces are going to play in to those distributions that are being used in that integral in the infect matrix that determine the effective R values that are plugged into that infect matrix. And then these last four pieces are if you'd like to run this model stochastically. So if you'd like to have a stochastic model with over dispersion, then you can set that Stoke parameter equal to true. And if that parameter is true, then you can specify these other parameters, theta, n underscore inf, so number of infections, or n iter, the number of iterations that you'd like to run for each parameter value. So just as a simple example, I could, for example, plug in a specific alpha value here. And so if you recall, alpha is the percent of infections that are asymptomatic. And so based on all the other defaults, if I have an alpha value of 0.3, you'll see here in the output, it's going to give me this nice data frame that contains all of the values for each of the parameters, as well as the R effective and the proportion identified. And so here I've set my alpha value to 0.3, and so you can see that that is in fact what the alpha value is in my output. And then we can look at the R effective, which is going to be that effective reproductive number that we're interested in. And given all of these, the default values along with an alpha value of 0.3, we end up with an R effective of 2.37. And so looking at this output, I can see that the default R is 2.5. And so based on this contact tracing program, we're reducing the number of onward transmissions from 2.5 to 2.37, just based on the test trace isolate program alone. So another nice feature of this particular function is that you can actually plug in vectors of values across these parameters, and it'll basically show you the entire grid of potential R effective values that will come from that. And so as an example here, I've plugged in 3 values for alpha instead of just 1. And that results in a data frame with 3 rows, 1 for each of these alpha values. And so all of the remaining parameters are just going to still be the defaults here, but of course I could set those myself too. I could either set them as the individual parameters, so that'll be constant across all of these 3 rows, or I could set them, I could also set a vector of potential parameters, in which case it will create a grid that will look at all possible combinations. And so here I've set alpha to 0, 0.2, and 0.3. And so 0 means that there are no asymptomatic infections in my community. 0.2 means that 20% of infections are asymptomatic. And 0.3 means that 30% are asymptomatic. And so then that corresponds to an R effective. And so in the case where there are 30% asymptomatic infections, our R effective ends up being 2.37. When there are 20%, it's 2.36. And when there are 0, it's 2.35. And so that sort of lowering based on that alpha is largely driven by 3 different things. The first thing it's driven by is this kappa value. And so kappa alone, that's going to be dictating basically the relative transmissibility of an asymptomatic person. And so we assume that asymptomatic people are half as likely to transmit as symptomatic people. And so if that were the only parameter that were influencing this, we would expect the R effective to be increasing if we have fewer and fewer asymptomatic people, because you would expect there to be more transmissions in the cases where there are fewer asymptomatic people because asymptomatic folks transmit less. So that's the kappa value, but then it's a little bit at odds with these other two values, rho S and rho A, which you can't see in this table because the table's too large to print all of them. But rho S and rho S here, that's the probability of detecting a symptomatic person, and rho A is the probability of detecting an asymptomatic person. And the defaults are 0.1 and 0.05, and so basically 10% of symptomatic infections are detected and 5% of asymptomatic infections are detected. And so because we're detecting, it's easier for us to detect symptomatic infections. If there are more symptomatic infections out there, we actually end up lowering our R effective by having more of those out there. And so that's sort of that interplay between each of those. But of course, if we change to different default values, then that relationship would likely change as well. All right, so now that we've talked about the R package and the model itself, I'm going to go a little bit into the Shiny applications, so some of the behind the scenes for ConTESSA. And so this is what it looks like if you open the application in your web browser. ConTESSA stands for Contact Tracing, Evaluation, and Strategic Support Application. And I'm going to just step through a couple pieces here in case you're interested in sort of learning how to program a Shiny application like this. And so the first thing I'm going to talk about is basically how you can have multiple separate pages. And essentially what this is creating like a dashboard framework. So I'm going to show you some simple ways to be able to create these kind of Shiny dashboards. And then I'm going to show you how you can generate reports. And so one piece of this that's really nice is essentially the user can click through these different these different pages. They can see a dashboard, and then they can actually generate a report that will create either a Word document or a PDF that they can then save a kind of a static version of to refer to later. And then I'm going to show you also how you can save inputs. And so this is basically going to show how you can download a set of inputs. So if users kind of input different values, this allows you to download a file that can save all of those inputs if they wanted to come back later. And we also have the ability to basically load those inputs back in. All right, so this whole framework is based on Shiny, and in case you're not familiar with Shiny, this is basically a way to be able to build interactive applications using R. And so this is kind of the main framework for a Shiny application, and in particular a Shiny application that you'd like to have a dashboard framework. And so I'm using two packages here. I'm using the Shiny package and the Shiny dashboard package. And there are two main elements to a Shiny application. You have the UI, or the user interface, and so this basically dictates what the person who comes to the application will see. And so that's kind of this part here. And so in order to create a dashboard, you're going to specify this dashboard page function, and then you'll specify different options in the dashboard header function to be able to update the header. So that's how I was able to get these logos in the header. That's how I sort of was able to dictate the colors of the header and things like that. And then to update this sidebar here, you use the dashboard sidebar function. And so that's where I have these different links to the different pages that are available on this dashboard, as well as some buttons, like to be able to generate the report or save inputs or load inputs. And then finally, the place where you're going to have kind of most of your code is going to be in the dashboard body, which is going to dictate kind of what goes in the main body of the application. So that's the user interface. And the second part of Shiny applications is the server. And so the server is where kind of all of the guts or the behind the scenes things that are running, our code that's running, models that are running, and things like that. That goes in the server part. And so that's what this little ... here is for. And we're going to be talking about a couple pieces that you can stick in there to sort of highlight some of those things that I mentioned that are kind of unique about this application. And then finally, to run the application, you use the Shiny app function, where you call the UI object that you created for the user interface and the server object, or that function that you created to be able to run all of the different behind the scenes pieces. Okay, so how do we actually generate a report? So the first thing you're going to do if you want to create a report is to create a .rmd file or an R markdown file for your report. And there are kind of two key aspects that this RMD file is going to have, because you want it to be dynamic, such that as the user interacts with your application, the report is dynamically changing, so that when they click Generate Report, it basically feeds in inputs from the application that they've been working through into that static report. And so to do that, you're going to use this params option up in the YAML, or the top part of your RMD file. And so you need to set these parameters, and these are going to be parameters that you're passing into this report from your application, so that it is dynamic and kind of taking into account user inputs, which I think that'll make a little more sense once I show you what happens in the server. And so you need to basically initialize those parameters, and so that's what I'm doing here. I'm setting those values to NA to initialize that I'd like to use those parameters in this report. And then you can do different things with those parameters. For example, here I'm just printing those values out, but you could include them in plots or tables or text and things like this. And so you access those parameters by name by using the $sign and indexing them from, there's this list. The params kind of come in this list, and you can say, for example, if I wanted to pull out parameter A and print it, I would do params $A. If I wanted to do parameter B, I'd do params $B, etc. So you save that .rmd file, and then you put something like this into your server. And so I'm going to use this function download handler, and I'm saving the output of this download handler function to the output. So that this basically, in Shiny, you create this basically list of outputs that you're going to reference in your UI. And this one I'm going to call report. And so I'm essentially creating this file. This report.rmd file is what I just created in the previous, on the previous slide. That's the one that had those parameters in it. I'm just going to copy it to a temporary file here. And then I'm going to pass the parameters to this file. And so what I'm doing here is I'm basically passing the A and B parameters that I used in that .rmd file into that, from Shiny into that .rmd file. And so I can use inputs that the user actually input. I could also alternatively use kind of other variables that I created as part of my Shiny server. And this allows me to basically pass those into that report. And then finally, I just render that report by using the R markdown render function. I have the file is the file that I have set. And the parameters here are going to be the ones that I've listed above. So that's how it works in the server, and then we need to have it in the UI so that the user can actually see something to be able to generate this report. So in the user interface, in the dashboard sidebar, that's where my report button lived. I use this download button function, and I make sure that I set that download button. I set that to be report so that it we know that it's going to generate the report that I've requested here. And so that report is going to be that's going to be the same name as what I've set called the output from the server. All right, so how about saving inputs? So this is also going to use the download handler function. Now I'm going to call this output, I'm going to call this save. And so for this, the main function that we're going to use is this reactive values to list. And so what that does is this input list is basically everything that the user has input via different text inputs or slider inputs. And it's going to basically take those values and it's going to stick them into a list. And then you can do whatever you want with the list. For example, I put mine into a YAML file, and then I allow the user to download that. But you could put it into any file format that you'd like to be able to let them download basically a list of their inputs. All right, so I'm going to give you a quick demonstration of the ConTESSA application in action. Before I do so, I just want to mention that we actually have a Coursera class that's free that goes over basically how to use this application in great detail. And so if this is something that you're interested in, feel free to check that out.